In this video I would like to present our experiment Coulomb's law. What you can see here is all the necessary equipment to perform the Coulomb experiment and to finally derive the Coulomb formula. So what you can see here is the two charged spheres, a force meter and our positioning system to change the distance between the spheres. On the left side you can see our electrometer to determine the charge of the spheres, and here on the right side you see the high voltage power supply and the charge storage capacitor to charge the spheres. I will explain how to derive the formula, and that will be done in two steps. First of all, we will investigate the dependency of the Coulomb force on the charge of the spheres, and in the second step we will determine the dependency of the Coulomb force on the distance between the two spheres. This will finally lead to the Coulomb formula, and we are able to determine epsilon 0. In the first part of the experiment we want to investigate the dependency of the Coulomb force on the amount of charge applied to the Coulomb spheres. This is done with this electrometer, and to investigate this dependency we need to know which amount of charge is transferred to the spheres in dependence on the high voltage applied here. How to transfer different amounts of charge to the sphere and how to measure the amount of charge on the sphere is explained in a separate video for the electrometer, but I will explain it here briefly so you can perform the Coulomb experiment. So we use the high voltage power supply, and let's start with 5 kilovolts. So it's switched on, it's grounded to the protected earth. It's important to wear this grounded bracelet if you work with the Coulomb sphere to avoid electrostatic influence of yourself. Then you use the charge storage capacitor, which is grounded too, and you charge this device positively if you put it in here. Now you can charge the sphere, and to determine the amount of charge, just take it out, put it into the Faraday cup and read out the voltage on the multimeter. It's 1.02 volts in this case. It's very important to discharge the Coulomb sphere before. There's another grounded cable here, so you can discharge the sphere. Further, discharge the Faraday cup in case you transferred some charge from the sphere to the cup. Now you can perform the same procedure, charge the sphere again and measure the charge with the electrometer. As shown in the other video how to measure the charge of the spheres, you can also charge the spheres negatively. This is done with the same high voltage power supply. You charge this side positively, and now you just change the ground to the red side, and now you charge the sphere with the blue side, and now the sphere is negatively charged.
We have performed this experiment with the largest of our spheres, which has a diameter of 38 millimeters. First, the high voltage is set to e.g. 5 kV on the high voltage power supply unit. As shown earlier, the spheres were first positively charged. With the electrometer, we are able to determine the amount of charge on the sphere. Therefore, the voltage at the capacitor has been measured. This voltage multiplied by the capacity of the capacitor used, here it is 10 nanofarad, gives the amount of charge that has been transferred to the sphere. When plotting the transferred charge amount versus the applied high voltage, a linear increase of the charge is observed. This result will be used in the next step of the experiment, where the dependence of the Coulomb force on the charge amount is investigated.
In our case, the force meter is a usual balance which has been modified in a very special way. We have some leverage here, and the force is directly measured in Newton. I will explain that later. First of all, let me show how to install the Coulomb sphere. Just do this and put the Coulomb sphere in here. Use the screw to fix it and put it back. It's very important not to touch the sphere itself, and if you use the spheres, clean the spheres before with a soft tissue and distilled water. Okay, let's go into details. Before using the force meter, make sure to remove this black ring here, which protects the balance. Here you can see where the force is measured, and here you see the leverage, which has a factor of roughly 10. So now you switch on the balance. If the balance doesn't show 0, put Tare to set it to 0 and make sure the mode is in gram. Due to the leverage, 1 gram is 1 millinewton and milligrams are micronewtons. So the balance is able to measure forces with micronewton. Therefore, we need to set this distance correctly. How to use the positioning system 400 is explained in an extra video, but I will explain it here briefly so you can set up your Coulomb experiment. In the Coulomb experiment, the spheres are treated as point-like charged spheres, so it's important to set the distance between the two centers of the spheres. So I will drive this sphere just next to the spheres, so they are aligned in a line here, and I will set this as the 0 in my experiment. So I press the two red buttons at the same time and my position is here 0. Now I move back 38 millimeters as we are using the big spheres and their diameter is 38 millimeters. So I press the back button and 3 times the 10, 5 more millimeters, 1, 2, 3. So our position is 38. I move our force meter now into this line, and this is my position where the 0 is the 0 between the two centers of the spheres. For determining the influence of the charge on the Coulomb force, we move back to a position of 130 millimeters. So I need to move back 2 more millimeters to 40. I move back 50. I'm at 90. And now I move to 130. Okay, let's measure the Coulomb force between the two spheres. The centers have a distance of 130 millimeters, but before we start, some important information. So make sure the spheres have been cleaned, and it's very important to ground the whole setup. So it's important to ground the remote control of the positioning system. The same ground has this ground bracelet. You need some grounded wire to discharge the spheres, and you need to ground the high voltage power supply and the charge storage capacitor, all with the same ground. Let's start the measurement. So we start with 5 kilovolt. We charge the capacitor here. And now it's important to charge this sphere first. Make sure it shows 0, otherwise press Tare to set it to 0. After that, you can recharge the capacitor and charge the second sphere. Now read out the value and you see you have 95 micronewton is the force between these two spheres if we charge them with 5 kilovolt. Now let's charge spheres with a higher voltage, but before, discharge both spheres with the grounded cable and discharge the capacitor. So we switch to 10 kV. Charge it. Make sure to switch it off as this high voltage power supply is not meant to run permanently. charge this sphere firstly. Okay, again it's at 0. Charge the capacitor again and charge the second sphere. Now we see if we charge the capacitor with 10 kilovolts, now we have a Coulomb force of 119 micronewton. You repeat this for all kilovolts, 15 kilovolt, 20 kilovolt, 25 kilovolt, and then you have to evaluate your results.
The charge quantity was determined in the first part of the experiment as a function of the high voltage. The resulting linear fit is used for further analysis. So we take this formula for calculating the charge on the spheres, as you can see in the new Excel sheet. As the two spheres are identical and have been charged the same way, their amount of charge is the same and is defined as Q. If plotting the measured Coulomb force versus the charge, that's shown on the left graph, it looks like a quadratic dependence of the force on the charge quantity Q. To confirm the quadratic behavior, the Coulomb force is plotted versus the charge to the square, as shown in the right graph. And here indeed, a linear behavior is shown, which confirms the dependence of the Coulomb force on the charge to the square.
First of all, in this video, everything is very compact here. In your experiment, please make sure to put everything as far away as possible to avoid electronic disturbances. We will perform this experiment and charge the spheres here with a high voltage of 15 kV. So first of all, let's charge the spheres. Again, we start with this one. If the balance doesn't show 0, press *, but now charge the second sphere. And make sure the distance between the two spheres is adjusted as explained before. The charge transfer to the two spheres at 15 kV is well known from our previous measurements with the electrometer. But for a determination of epsilon 0 with high accuracy, we recommend to measure the actual charge on the sphere with the electrometer again. You just take the electrometer, make sure the Faraday cup is discharged, and just put it over one sphere without touching the Faraday cup. The multimeter shows 3.07 volts, which corresponds to a charge of 30.7 nanocoulomb. You can do the same with the other sphere. Again, make sure it doesn't touch the Faraday cup, and here we read 2.72 volts. And now you can later calculate your epsilon 0 with these two values. So right now the distance between this center of the sphere and this center of the sphere is 200 millimeters. We start this measurement at 200 millimeters distance because we get a high accuracy of our force meter. If we start further away, the accuracy wouldn't be that good. To start the measurement, we now move in 10 millimeter steps towards that sphere. And this has to be done really quick in the experiment and not as slow as in this video to get good values. So here at 200 millimeters distance, we get a value of 217 micronewtons. And now we move 10 millimeters towards the sphere. The force is increased and we get 246 micronewtons. We move further and further, and we move in 10 millimeter steps up to a distance of about 110 millimeters. If we get closer than 110 millimeters, we get some electronic induction on the spheres and the measurement values are not correct anymore. Now you can calculate epsilon 0 and derive the complete Coulomb formula. If you want a higher accuracy for your epsilon 0 and better statistics, you can repeat the previous measurement with different high voltages to charge the spheres. In our analysis, we use 10, 15 and 20 kilovolts. As you have seen, the measured charge amount of the two spheres were different. The value of 2.72 volts of the sphere on the right side was lower than it should be. The reason for this observation is that the discharging has already begun due to our long explanation in this video. This shows the importance of performing this experiment quickly.
We used the largest spheres with a diameter of 38 millimeters, which were charged with the high voltage power supply set to 15 kV. The extra measurements with the electrometer results in a charge amount of each sphere of 31.3 nanocoulomb, which fits very well with the results of the charge determination shown in the first part of the experiment. In this example, the measured Coulomb forces are shown for distances of the spheres between 110 millimeters and 200 millimeters, with a step size of 10 millimeters. In the upper graph, the Coulomb force in micronewton is plotted versus the distance of the spheres in millimeters. It looks like the Coulomb force has a dependency on the inverse of the distance to the square. To verify this assumption, in the lower graph the Coulomb force is plotted versus the inverse of the distance to the square, and indeed, a linear correlation is confirmed. This is the next important result. The Coulomb force is proportional to the inverse of the distance of the charges to the square. In this graph, the Coulomb force and the distance are shown in SI units, Newton and 1/meter squared, as this is needed to determine the dielectric constant epsilon 0. A linear fit has been done to the data. Here the slope is equal to the charge to the square divided by a constant. As we know, this constant is written as 4 pi times epsilon 0. As the charge is known in our case, 31.3 nanocoulomb, a rearrangement of this equation to epsilon 0 results in an epsilon 0 of 8.72 multiplied by 10 to the power of minus 12 ampereseconds per voltmeter. This is very close to the literature value of the dielectric constant, 8.85 times 10 to the minus 12 ampereseconds per voltmeter. For better statistics, one can derive the epsilon 0 from several measurements with differently charged spheres. In our case, the spheres were charged with the high voltage power supply set to 10 kV, and in another measurement set to 20 kV. The average of the three resulting epsilon 0s is shown here, and the deviation of this average value from the literature value is smaller than 1%, which is a really fantastic result. The dependency of the Coulomb force on the charge on the distance of the charged spheres has been shown experimentally, and the dielectric constant epsilon 0 has been determined.